Our next speaker is from Cadence, Deepak Gupta. He's a senior services manager for application engineering. Deepak Gupta is working as a senior manager in systems and advanced verification group at Cadence Design Systems in India. He's responsible for proliferation and deployment of Cadence tools to customers in India. During his 17+ years of experience in industry, he has held multiple positions with both product R&D and the field organizations. He was instrumental in the setup of VLSI design centers, development of various ASIC intellectual property cores, and also driving adoptions of newer systems and verification methodologies to customers. So I'm going to hand over to you.
Thank you, Mike. Good afternoon, everybody. So let's do one thing. Like in this session, I will try to take you through how the verification and the systems space has progressed so far, and how we are going towards the future, how it looks like. So let's start with what we have seen in last 10 years. So in last 10 years, in fact, when I started my career, it was only the simple two languages, VHDL and Verilog, and the world was divided over that. Now, in last 10 years, things changed a lot, and languages like E or Vera and those things evolved, and our verification environment started to look like where we were having the coverage monitors, we were having the checkers, we were having the stimulus, and all things were there, right, to use and basically make the better decision on the coverage and the closure of the verification. However, what has changed a lot over the last 10 years is this design IP. So if you look at this design IP, previously the designs used to be get developed in-house, and they were basically very targeted to some specific application, and they were very custom to that particular company or that particular application, and they were themselves as IP. Now in recent past, what has happened is these designs have changed a lot. Now people are basically looking at taking the IPs, bringing it to the subsystem, integrating all of those, and coming up with the SoC. And not even that, when they basically create those SoCs, they use those SoCs as a subsystem and then take it to the other designs also, right? Within a chip nowadays, there are multiple instances of the subsystem. So this entire gamut, which has happened in the last 10 years, has basically created a complexity for the verification engineers a lot. So we will look into that, right? Where we are spending more time and all. So the complexities which has increased over the period of time is we have seen in last at least 4 or 5 years since we saw the iPhone launch, right? The applications are flooded in the market, and there are a lot of applications coming up with in the different verticals, and market has a lot of application, and everything is getting driven out of application nowadays. So the hardware what we work on, the hardware we design is coming out of the application. So everything is driven by the application. So a lot of applications are there, a lot of software is there. The industry is moving towards the use of the standard-based protocol IPs, right? Nobody wants to basically write their own custom designs. Nowadays, they want to see if they can somehow reuse the readily available IPs from the market, which are proven on various chips, and come up with a good SoC and meet the time to market. So all that is again adding a complexity, because if you look at, if you're acquiring a component from third party, then you don't know what environment it was tested, how it was developed, what methodology they have used. There may be a compatibility, there may not be compatibility. So altogether a different set of complexity it brings in to integrate in your SoC. On top of that, if you look at the handle market is growing, and which means the power has become very critical, and every design, every handle device works on battery, and battery needs to be optimized. So a lot of demand over there. They have high speed interfaces like PCI Express or USB or it can be a wireless also. Then in that case, the analog becomes more critical, and which creates more complexity for the digital as well as the analog guys to work on the SerDes or to get interface with the digital block. Debug, that is a big challenge, we all know. We all spend quite a lot of time on the debug. More than 50% of the time we are spending on the debug nowadays. And that is mainly because the SoCs have grown a lot. They are pretty big, and now We are looking into each and every aspect of the SoC. If there is a bug, then going to the root of the bug is becoming a big challenge. Application and user driven requirement. We talked about the applications, right? So now one more thing is happening is people are designing a chip which is little generic in nature so that they can target it to the different verticals. I will give you an example. So it should be very good, and it can't go with that. So it's a mission critical application. The other one, tablet, where you can handle the tolerance or the fault you can handle, but you will have to basically look at more applications and all. So two different requirements, same chip is going, and then again it adds to the more complexity in it. We all know about the sinking time and money and the link between the time and the money a lot, right? So I'm not going to talk about that. Now, to cater all these complexities, now how industry is evolving is, till now, we were working mainly on the C development, which means the hardware guys will start first, then somewhere at one point, the software guys will start, and then we will deliver, which takes close to 2 years. Now, which is not going to work out, because if you look at the product life cycle, it is shrinking. So we need to come out with our product very fast. To do that, what we need to do, we need to make things parallel. And how we achieve this parallelism is bringing the software development in parallel to the hardware. We'll explore more on that. On the IP side, since IP story is becoming pretty big, now most of the people have become the SoC integrator. And 80–90% of their chip is integrated from the IPs, and rest they develop their custom logics. So debug, we talked about, it is one big challenge. So we all have heard that for any given project, we spend close to 60–70% of the time on the verification. There is another study which is pretty interesting, that how we spend the 60–70% of the time. It's not test creation, it's not execution, which we all feel that the compute takes a lot of time, but really it is not. It's more on the debug side. So if there is an issue, then again, in that case, the human gets involved in it, and again, it takes time to close and all. So debug, we are spending more than 50% of the time on that. And how industry is trying to reduce it is, till now, like I will say till recent past, everybody used to debug at the signal level. Let's say like if you have a bug in a chip, then people will start from the one end of the chip and slowly start to go inside the chip and see inside the design and see where the bug lies. There are other technologies to pinpoint you on that, like assertions and all, but they also had the limitation. But now what is happening is, yes, that challenge will always be there, that somebody will have to go slowly inside the design to root cause it, but how we can make it more easy for the debug or time saving for the debug is the transaction based or the class based verification, which UVM or the methodology like UVM or the OVMs are providing. The base set which comes with UVM or OVM provides you all the hooks you need to fasten your debug cycle. You need not to look at the signal, you just look at the transaction, which are normally generated through the verification environment of the verification IP, which you are using at interface, which you can trust on. So the debugging has become more fast. So let's look at how the development of hardware software verification going along. So this is the diagram for the serial hardware and software development, where both hardware and software people started at the same time. However, the spec was generated for them, and then after that, software guys wait till the RTL comes in hand. Once the RTL is ready, they will start writing the firmware, and they will take it to some emulation platform or FPGA platform, where they will try to verify it, whatever they have written, and after that, once the chip is back, they will put it on the prototype board and test it, and that is how it goes out. But how we can optimize it? So what we have done is, or the trend is today, is to somehow bring that entire software development cycle upfront. So the moment we have the spec ready, we need not to wait for the RTL. What we can do is, the software guys, they know how the model looks like. then they can start working on the subsystem, which is a virtual prototype subsystem or a virtual prototyping subsystem, which is based on the PLA models. They can start development of the software on that. Although it will not be completely functional, whatever they have developed, it will not be fully tested because there is no timing information in that. But the 60–70% of the time on planning, coding is already done. So once the RTL is ready, they can come in, they can test it, and they can move ahead. So once their RTL is ready, they can start writing the diagnostic. Sorry, they can start testing the diagnostic and firmware and prototype it on the emulation platform or on the FPGA platform. And once again the chip comes back, they can test it, and then it is gone. We have seen typically people save close to 6 to 9 months time on this if they basically follow this cycle. The other advantage what people also get is, if you notice in the previous one, if there is an issue in the firmware if it is because of the some wrong hardware, then the only way out is the respin. In this case, what can happen is, because both of them are going together, the bugs can be resolved together and it will not go up to the respin of the chip. So let's look at what platforms are there at this moment in the industry to cater all these needs. So one is the software development toolkit. We all know that this is the fastest way to develop any software. However, this is not as it is based on the behavioral aspect of the design, so it may not be that accurate. Virtual platform, here we use a model, we create the complete SoC using TLM models for whatever blocks you have, then you develop a software. It is very close to the real RTL, but no timing information in it. So again, you will have to basically wait till the RTL comes in. Then we have RTL simulation, we all are familiar with. It's more time consuming, it's accurate because it's running on RTL, we know what is happening, but it's very slow. So that is where the FPGA prototype or the emulation or acceleration piece comes in picture. To the hardware, you emulate it there and then interface with your software test bench or the system Verilog or UVM test bench. Then once the silicon is back, you can do the prototype on a prototype board. The accuracy is very high because you are using your chip on that particular board and you are testing your software. So it's very close to the application or whatever you need it. So main challenges. Now we have seen these 6-7 solutions what we have in the market right now. But one of the biggest challenge happening right now is how to connect all these different platforms together. Software guy is working in one domain, hardware guys are working in one domain, and emulation guys may be working in another domain. How to bring the debuggability in between all those platforms? That has become a big challenge. So people are basically working towards addressing that particular requirement. The other thing is, since people are using IPs, right? Sometimes what happens is, and people when they're using IP, they consider themselves as a SoC integrator. But what happens is, when they bring in the third-party IP into their SoC, it brings in the new challenges, right? For example, I will take, we all know about the Ethernet, right? And plugging Ethernet IP to a SoC seems to be very simple, but it is not that easy as it sounds, right? It's the person who is integrating the Ethernet, he will have to use the Ethernet, he will have to look at the PHY, how it works out, what protocol, what interface type they need to use, PCS, then integrating it together, verifying it in separately as a block level, then bringing it to the SoC. So it's altogether a different challenge there. We talked about the application part. So just to give you a feel how the applications and the hardware is interlinked. Actually, I own Samsung S3 phone, right? So when I bought it, I was really very disappointed. I saw many features when the product was launched. But what was happening is, within a half a day or a 1 a day, but the battery was dying out. I had no clue where the problem is, whether it's a hardware, whether it's a software. I thought as a normal person that yes, it is a hardware issue, it's a battery problem, it's not something where software guy can or apps can do it. But After a few days, I saw an update from Samsung, and they updated my device to Android ice cream sandwich. And after that, it is working fine. My same device is able to hold the charge for 2 days. So that is how the hardware has linked to completely with the software. So we will have to basically make sure that, okay, like whatever application, whatever hardware we are doing, they are closely monitored, they are properly architected so that we are getting a better performance. So how the EDA industry in general is coming to cater this all need. We talked about how the virtual platform helps. We talked about how simulation environment works. We talked about how acceleration or the emulation platform works. And we also talked about the FPGA platform. But we also talked about is at the same time, they all work in separate isolation. So how to deal with it? So now what the EDA industry is moving towards is coming up with a system development suite. So what they are providing is a single window solution for all these products. So the person who starts with the virtual platform, can slowly move towards the FPGA platform. All of them will share the single window for the debug and all. So that gives a immense advantage to them. And this is normally people are calling it as a hybrid model where software as well as the hardware is getting developed together and all are interlinked. We will see how it is getting enabled. So if you look at one of the challenge we talked about is a debugging in between all these different protocol platforms. And so what EDA industry is coming up with a single window solution where, let's say, like you have hardware pieces inserted, you have virtual platform or the models inserted, and some software development is going on this. And this development happens with the same GUI interface, and you are looking at the same signal window which you see, the hardware guy sees or the software person sees. So that's an immense advantage. If there is a problem in the software, then the software engineer can go and talk to the hardware guy and pass it easily because they are sharing the same window. The other thing what is happening is on the VIP side, there was a question in the forum that if that was more on the how we basically take the synthesizable VIP to hardware, and if there is if it is not mature or something like, then it will be a problem to see like whether it's a problem in the design which is under test or it's in the VIP. The VIP is basically nothing but a piece of software or basically a verification environment for a given protocol which is already proven with different vendor and is mature enough. So at that point, the person will have to basically evaluate the various VIPs available in the market and see which one is mature and then use it. So the risk is reduced. So there are VIPs coming up for running in the simulation. There are VIPs coming up to run at the TLM level. There are VIPs coming up to go in the hardware itself, the synthesizer VIPs. System integration automation. There was another question that how we can stitch the environment together, how we can write the sequences automatically by analyzing the holes in the verification, right? So we are moving towards that. People have solutions towards where they can take up the SoC spec. The SoC can be stitched together and the entire verification environment can also be stitched together. The technology is under development. Some people have already released, some people mature. It's getting matured over a period of time. These subsystems which are coming out of this automated generation of the complete verification environment right now are getting used for the complete verification as well as for the performance analysis also. Application-driven system verification. So we talked about how the applications are important for the hardware. So what is also happening is people, those who have already started on the virtual platform, they have the utilities in hand with the test cases directly for the hardware guys. So when they're running the application, they know what are the scenarios going towards the hardware. At that time, the person can dump out the C test cases, which can directly run on the hardware. So that technology is also evolving a lot. And I think it's not much time, within a year time frame, that you will see all those things coming in the market. And on top of this, verification planning and management, that's a major aspect. We will have to have a feedback-based verification management process where you look at what is your verification, what are your verification goals, where we are, where we need the tweaks, and keep doing that feedback unless you basically achieve your desired result. That's pretty much for me.
Do we have any questions for Deepak before lunch? Any questions on the cadence one? We have some time if there's a question from the audience at all. Okay. Okay, thank you, Deepak.